Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and we're back for part 2 of Brian Mullin's On Gravity. We discussed Newton in the last episode. Today we're going to discuss the Cavendish Experiment. Now, Brian has some very bizarre thoughts on the Cavendish Experiment. I think that it would probably be better for you to hear it from his own mouth, because if I say it, you'll say I'm exaggerating. So let's cue up the music and get going.
Henry Cavendish was very wealthy, and he did a lot of things apparently. I've listened to some very respected physics teachers praise his work, and I've studied some of his work, but mostly what I was interested in was how he determined this gravitational constant. He set up an experiment. Let's go back to where we just have these two equations. You know, they haven't figured out the big G yet. They do know the radius of Earth, though, because they knew the circumference. So they knew the radius of Earth, but they didn't know big G, and they didn't know the mass of Earth. Okay? So going back to Cavendish in 1798, Cavendish built this box, this wooden box on his property. Okay? And in this box, there was a pulley with a rope leading outside the box, something like that, a little handle on it. And what hung from it was this thing called a torsion rod. It's something like this. And on the ends of the rod were these large lead balls. And on the inside were these smaller lead balls. He used lead because it's very massive, it's very dense.
You know, I'm sorry for stepping in again, but if you're going to talk about the Cavendish experiment, Brian, at least draw it correctly. Let me show you what the Cavendish experiment really is. All right, let me give you the basics of the design of the Cavendish experiment. Now, indeed, Cavendish was rich. Cavendish had a big garden shed. Cavendish built a box in his garden shed. It was huge, had 2-foot thick walls to try and isolate it. So what happened was he had a very solid beam, and from it hung what was called a torsion balance. Now here's the way the Cavendish experiment works, and it's a very simple, but as you say, rather difficult and precise experiment. This is from the side. We've got the torsion balance and the large masses and the small masses. Here's looking at it from the top. So the red right here, that's the torsion balance, the wire. These are the small masses at the end of these arms. Next to them are large masses that are on a platform that can be swung perpendicular to the two small masses or in close proximity but not touching. Now, mass attracts mass, and as a result, these small masses, which can twist on that wire, will try and go closer to the large masses. Now, the thing that prevents them from going all the way to the large masses is the twist in the wire, in the torsion balance. And that can be measured. So by figuring out how much torsion it took to oppose the attraction of the masses to each other, that was a direct measurement of the attraction between those two masses. It was a brilliant experiment, and it's repeated on an annual basis in practically every university in the world in their physics department. As a matter of fact, my friend Blue Marble Science built a scale model of Cavendish's experimental apparatus in his garage in Tennessee. And he regularly live streams it and measures G. I'll provide you a link for that in the description because it's well worth your time. It's kind of like watching paint dry as it swings back and forth and oscillates. But you can clearly see it demonstrates mass attracting mass, and it measures what that attraction is. And by knowing the attraction and the masses, you can determine G. But that wasn't Cavendish's plan.
There's a force of gravity between any two masses, not just the Earth and us. All masses have a force of gravity on each other, or create a force of gravity on all other masses based on this equation and the proportion that Newton came up with. Well, when I started researching this, I said, okay, well, let's let's see some examples of a modern day torsion rod experiment that somebody's built that shows how this works. Well, I couldn't really find one.
Now, a friend of mine named Blue Marble Science is a retired engineer with some woodworking skills. And in Tennessee, in his garage, he built a working model of the Cavendish experiment. I think it's on a 3/5 scale. And he regularly live streams it and measures G live. So I think rather than let Brian continue to have all of the attention here with his nonsense, I think we're going to shrink him down and put him down in the lower right corner. And in the background, I'm going to go ahead and have a video of one of Blue Marble Science's Cavendish experiments, because I think it's kind of funny to have him claim that it can't be done while showing it being done in the background. That's just my personal amusement.
I actually had a lot of trouble finding one. Actually, one of the physics professors that was praising him had a little model that he held up and was joking that his TA couldn't get it to work and got frustrated with it and gave up. And I'm thinking to myself, over 200 years later, we don't have models of this, or repeats of this experiment all over the place that determine big G. It didn't make much sense to me. So I said, okay, well, going back through the history, let's assume that he did this somehow. He's a really smart guy, and we just haven't been able to get it to work again. Okay? So, Cavendish determined big G through that torsion rod experiment. Okay? So he calculated it to be the value that we're still using, which is 6.67. 408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? He determined that from that experiment. Let's assume that's correct. So now he must have been really excited because he knows what this big G is. He knows what his mass is, or any other mass of an object on Earth. He knows what the radius of Earth is. So he can set these two equations equal to each other. He knows that weight and the force of gravity are equal. So what he did was, you can look this up, this is exactly how this was done. Weight, which is equal to mass times G, or the mass of the man, or whatever object he's using, in my case I'm going to say me, is equal to big G times the mass of the man times the mass of Earth divided by the radius of Earth squared. Now immediately you can cancel the mass of the object, or me, out, because they're in the numerator on both sides. This is really mg over 1. Okay? And now, let's come up here. You can solve for the mass of Earth. You can multiply the radius squared times both sides, and that comes over here. Cancels on this side, and then you can divide by big G. So you get me, and this is basic algebra here, is equal to little g, the acceleration due to gravity, or the rate at which things accelerate towards Earth, times the radius of Earth squared divided by big G. And that is how the mass of Earth is calculated. That is the mass that NASA had on their fact sheet, where I got all this information about the Earth's radius and the mass of Earth and everything.
It's amazing how badly he screwed that one up. Brian Mullins apparently has never read the Cavendish experiment because he has no idea what Cavendish actually did. For example, Cavendish did not calculate little g. Cavendish did not calculate big G. What Cavendish did was measured the force of attraction between two masses of known mass. And he used that to find the specific gravity of the Earth. Once he had the specific gravity of Earth, he could actually get the density of the Earth. And that was his goal, was he wanted to measure the density of the Earth. That was a great question in the late 18th century. He answered it, and he answered it well, and that answer has stood up to the test of time. Now, even though Brian is screwing this up pretty badly, he does get some things correct in the next section. So I'm going to let him explain that, and then I will explain the correct interpretation of that and show why his is wrong.
So I looked at this and I said, okay, that makes sense, but I still had the question in my mind saying, wait a second though, you know, why can't we do this torsion rod experiment now? You know, there's some, I looked into this more, and right now there's debate going on about what this big G actually is. Some people are arguing and saying it's different. And they're doing experiments on an atomic and a subatomic level where they're looking at particles with you know, very powerful microscopes and observing how they're attracted to each other, which they say is because of gravity. Now, I can't go buy an electron microscope and do those experiments myself to check it because I don't have that much money. And I don't want to try to build a torsion rod experiment because from everything I read, it sounds like it's not going to work. So I'm also going to spend a lot of money on that. So I'm really questioning, you know, this big G. You know, how did they come up with that? But then I started to look at this algebraic expression that was written. Get rid of big G again. Say, well, you know, what if they were so sure about this equation due to gravity, or this equation of gravity, that, you know, they were having trouble coming up with G, that they did something else to determine it. What if they did this? Or Cavendish did this? What if he said G is equal to the acceleration due to gravity, as he would have called it, times the radius of Earth squared times the mass, or divided by the mass of Earth. Of course, he doesn't have the mass of Earth, right? Well, he does have the radius of Earth. And at that time, they definitely knew how to calculate the volume of a sphere. They know that if they could figure out the average density of Earth, they could multiply that by this volume and get mass. You know, if you know, at the time they would have known the density of water and the density of sand, the density of ground rock, the density of iron, the density of gold, the density of silver, the density of all these things were already determined. And to determine the density of something, it's really just the mass per unit volume. For example, we'll call them rho. Call rho density. Rho water is equal to 1,000 kilograms per meter cubed. What that says is in 1 cubic meter, if you have you have something that holds a cubic meter of water, it weighs 1,000 kilograms. If you have something that holds 2 cubic meters of water, you say the density of water 1,000 kilograms times 2 cubic meters. You see the cubic meters would cancel. You get 2,000 kilograms is how much it would weigh. Okay. So you definitely know the density of water back then. You definitely know the density of, say, let's say sand and soils, and they definitely knew the density of iron. I mean, they were. If you use NASA's fact sheet with their mass of Earth, which is 5.9726 times 10 to the 24th kilograms, and you divide that by the volume of Earth, you will get an average density of Earth, I'm going to call that rho E over here, of 5,515 kilograms per meter cubed. Okay? So, looking at this, just looking at water and soil, you know, water is, well, the average density of Earth is over 5 times greater than the density of water, and water is actually pretty dense. The average density of Earth is 5 times that of water. It's also a lot greater than soil.
Now, Cavendish did indeed note that those were the densities of those objects, and he did note the density of the Earth at being very close to the density of iron. And that was one of the earliest pieces of evidence for the Earth having an iron core. But even though this all follows logically and makes perfect sense and is very well documented on, I believe, 18 different trials by Cavendish and tens of thousands of trials by universities in the years since, he wants to try and say that there is a question about what G is. Now, the only question that there is about G is kind of like the only question that there is about the distance from the Earth to the Sun. It's a matter of precision. How many decimal points out can you go? How many significant digits? You know, how far can you calculate pi? That's what the difference of opinion is when it comes to G. The fact that G is approximately that is not in question. That is confirmed by multiple other measurements, including the one from Blue Marble Science, got very close to G. And that was with amateur apparatus. Can you imagine what universities can do? We had another debunker recently go out and do it in a Faraday cage in a vacuum and got similar results. So Brian's faced with a difficult problem right now. He has to come up with some way to disregard this evidence. This is conclusive evidence of gravity. This is conclusive evidence of the mass of the Earth. It's conclusive evidence of the density of the Earth, and it's conclusive evidence as to what G, the constant of proportionality, is. So let's go see how Brian tries to hand wave this off.
So what I'm saying here is, if you follow where I'm going with this, how do we know they didn't guess, or that Cavendish didn't guess this mass of Earth, and then just use it to solve for G, and then do the opposite and say that he did this, that he solved for the mass of Earth using that value of G? It's the same thing, just based on the algebra. And then if you plug both of those values into this equation up here and use the mass of any object, whether it's a man, a horse, you know, a carriage, anything, and use the radius of Earth, you're going to get a force that's equal to the weight you get for that same object if you just multiply the mass of that object's time the acceleration due to gravity, or the rate at which acceleration at which things fall towards Earth. Seem far-fetched? I don't know. You know, the fact that we can't really get this experiment to work, this torsion rod experiment to work, is perplexing. Very perplexing. We have to trust that they didn't do this. But what if they did? You know, our entire solar system model stems from this. Assuming that this is correct. Assuming that this big G, this gravitational constant, is correct.
Now, to be honest with you, this is simply a false narrative. The Cavendish experiment has been repeated frequently. Blue Marble Science has done it. I personally know at least 3 people that have done it. Now, I haven't, because my field wasn't physics in college, it was biology. But I am familiar with the experiment, and I know the physics guys did do it. So this premise that Cavendish somehow made up G or made up the mass of the Earth and then made the stuff fit is absurd. It is completely indefensible and untenable. The other thing is, it's an ethical problem. One of the things about science is that you assume that when somebody reports a measurement or says they did an experiment a certain way, that's the way they did it, all right? You don't impinge on their character by saying they made something up. What you do is you do an experiment and show that they couldn't have gotten those results. That's the way you falsify something in science. I don't understand why Brian is conveniently forgetting that the Cavendish has been done. If he was a physics student, he would have seen it done in school. Now, the bottom line is, if Brian Mullin says he's never heard or seen of the Cavendish experiment being done, he's either lying or he's delusional, because he could not have gotten the education that he claims to have and has been verified without seeing a Cavendish experiment being done. You just can't get that degree and not be familiar with the Cavendish experiment and its modern renditions. So that's bad enough, but now he's going to go completely insane. And I almost hate to put this up because this is devastating to his reputation. But I think that we need to see it because it's part of the record.
Is that Cavendish and Newton were both Freemasons. It's a very big club, you know, and back then, the average person couldn't even write their own name. So people slowly were introduced to the sciences. You know, more and more people were introduced to the sciences over the years, and it wasn't just the wealthy people over the years. And I know there's a symbol out there that a lot of people have been trying to figure out looks something like this. You ever seen one of these before? Found one on a Freemason lodge. It's kind of ominous symbol. First time I saw it, I was like, what was that? What is that? It's very strange. Compass and a protractor. The big G in the center of it. What does that stand for? I don't know. Could just be a coincidence. Some people think it means geometry. Some people think it means God. I don't know. Some people even think it means Gnosticism. I've done a little research on this. Who knows? But maybe that's just a coincidence. I'm just asking questions.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me.